Hey guys, welcome to your chapter 19 Edpuzzle over global change. We'll obviously be talking about climate change and tying everything together with our previous chapter, which is all about air pollution. Maybe. There it is. So when we're talking about different changes that we're seeing around the world, we do want to make sure that we're being specific about what sort of changes and kind of what spans we're talking about. So we've got global change, global climate change, and then global warming. Now, these sound synonymous, but they're actually very different. So we're talking about global change. This is kind of talking about changes in general, natural or human cause. So we're talking about chemical changes, biological changes, physical property changes of the planet. These are natural, and this happens all the time. So when we're thinking about the huge change in global temperatures, including a giant drop in global temperatures causing ice age, that would be a global change, something that's happening throughout the entire planet. Whenever we're talking specifically, kind of a subcategory of global change would be global climate change. These are specifically changes to the climate of the Earth itself. We're thinking about overall weather patterns, overall temperature, precipitation patterns. When those change, again, it's a subcategory of global change, but it's a smaller subset to that. Finally, we have global warming. Again, another kind of inside category within global climate change. This is when we're seeing the actual physical warming of the oceans, land masses, and atmosphere. So again, we're kind of got big changes, global change, subset of that is global climate change, and then a subset of that is global warming, kind of giving you a scale of everything we'll be talking about. One of the big things we're talking about within global warming is the greenhouse effect. And the greenhouse effect is a natural thing. It's actually one of the reasons that we can actually live on Earth. We appreciate that because we like living here. But essentially, what's causing that, and I've got a picture coming up very, very soon, so sit tight on that. But within the greenhouse effect, we have five major gases known as our greenhouse gases. These greenhouse gases are important because they essentially take radiation from the sun, they reflect it back to the Earth's surface, and they're essentially making sure that the Earth's temperature is livable, that we've got a nice little 70 degree, 80 degree, 90, sometimes 100 degree, but essentially livable temperatures for human beings. What happens is UV radiation is coming down from the sun. As UV radiation comes down from the sun, it's either going to hit the ozone layer or it's going to hit the Earth's surface. Think about albedo and that reflection. Some of it that essentially is going to be hitting and reflecting off of the Earth's surface, or some of it that comes and hits the ozone layer, then converts it into lower energy infrared radiation. So we started as UV radiation, now we're infrared, so it's slightly lower energy. Again, that's one of the reasons that we have the ozone layer and why we consider it protecting us. That infrared radiation then goes back, reflects back down towards the atmosphere, towards the Earth's surface, or I should say, reflects back up to the atmosphere. Once it reflects up to the atmosphere, then it is absorbed by our greenhouse gases. We have five major greenhouse gases, four of them natural, one of them human caused. If it is absorbed by the greenhouse gases, then it is radiated back to the Earth. So essentially, we're creating a little box, an insulated box. UV radiation comes in, turns into infrared either when it hits the ozone or when it reflects the Earth's surface. No matter what, though, it's going to bounce back up to our gases in our atmospheres, our greenhouse gases. Those then absorb that infrared radiation, reflect it back down to the Earth's surface. So essentially, we have infrared radiation ping-ponging and staying down here. Infrared radiation is a form of, or radiation is a way of essentially passive heat transfer. So it is essentially creating a heating box, a little band of heat within our atmosphere and within the ozone layer. So kind of showing you a visual. Again, we got our incoming solar radiation in the form of UV rays. It hits the clouds, it hits the surface, or it is essentially hitting our ozone layer. Once that happens, it's converted into low range or low energy infrared radiation. Those will then reflect back up. Some of it does go way out into space. Okay, it goes away. But a lot of it, though, is going to be happening right here. This outgoing infrared radiation gets trapped by our greenhouse gases. Again, it's like an insulating blanket. It's preventing that infrared radiation to actually escape out. Most of it, we see big arrow. Most of it is staying here. Again, creating essentially a greenhouse for an entire planet, keeping our temperatures at a stable amount. Now, more greenhouse gases, though, the more that temperature is going to be. Again, we got five major greenhouse gases. These first four, well, I guess ozone, is also considered one sometimes. But anyways, the big six, but I usually think about, anyways, water vapor is a number one. Water vapor, again, completely naturally caused. Carbon dioxide, used to only be natural. Now it's also human caused as well. We'll be talking about that. Methane, another one of those that is natural, but also human caused. Nitrous oxide, natural, but also human caused. Ozone is kind of, it's not one of the big five, but it is still considered a greenhouse gas. And then finally, we have CFCs. CFCs, you might remember, big bad guy from air pollution. CFCs have to do with our photochemical smog. You might remember it also had to do, not with photochemical smog, my apologies. In air pollution, we learned that CFCs have to do with stripping down the ozone layer. So not only are they stripping down the ozone layer, but they're also a greenhouse gas, increasing global temperatures overall. So CFCs, you might remember. Even if we're looking at this, again, CFCs are just bad guys all over the place, because now we're looking at global warming potential. We're also looking at duration in the atmosphere. We did say that CFCs, because it's a man-made compound, is incredibly durable. It takes a really long time for it to actually break down. It has to be hit with X amount of infrared radiation to actually break apart that chemical compound. So because of that, look at that duration in the atmosphere. CFCs, again, really, really large. They have the greatest amount of global warming potential. Thankfully, they are only 0.9 parts per million concentration, at least in 2010, where when we're thinking about carbon dioxide, that's usually the one that comes to mind when we're thinking about global warming and greenhouse gases. We do see that carbon dioxide, while its global warming potential is not as large, it does have the greatest concentration in terms of our greenhouse gases. So we're kind of watching carbon dioxide, but again, we are also watching that CFCs because of their giant potential for global warming. There are some natural greenhouse gas causes. So when we're thinking about what's actually creating these, volcanic eruptions is going to be one of the main sources of carbon dioxide. Methane, as naturally things decompose, we are going to be releasing methane gas. Also, I mean, permafrost should not be melting. We'll be talking about why permafrost is melting and why that's a bad thing in just a little bit. But if methane gas is actually melting, that is also a release of methane. Nitrous oxide from denitrification. Remember, that's actually releasing it back into the atmosphere from the soil. That's our denitrifying bacteria, thinking all the way back to Q1. Finally, we also have water vapor as well. Just, evaporation, condensation is another way that those get up there. Human cause. Hey, this is a much bigger list. So burning of fossil fuels is going to be primarily producing carbon dioxide, but also nitrous oxide as well. Sometimes with mining, if it's fossil fuels that we're essentially harvesting from mines, that can also be releasing sulfur dioxide, which you might recall from our refinery talk when we talked about acid rain chemistry and the nitrous oxide and sulfur dioxide. Agricultural practices is primarily going to be releasing methane. I don't know how else to say this besides cow farts. The gut bacteria within our livestock, especially our cattle that have to kind of go through those multiple digestion cycles, there is a host of methane that is being produced during that digestion process. So the more cattle you have, the more agriculture you have, the greater amount of methane that's being released anthropogenically. Deforestation, primarily going to be releasing carbon dioxide. Think about all the carbon molecules. Carbon is the element of life. So when you're actually deforesting or cutting down trees in an area, going through that process of deforestation, it will be releasing carbon dioxide. Landfills, methane, a really big source right here. We're going to talk about landfills more in our second semester when we get to our waste management unit, but landfills during that decomposition process, especially if there's no oxygen present, it's going to be a huge release of methane. Refrigerators, we talked about this when we got to air pollution, that CFCs, aerosol, I'm always thinking about aerosol coolant as our CFCs. And finally, industrial production, again, CFCs, the ones that we're really watching out for. I know I'm going fast. I'm just trying to make sure this isn't like a 40-minute video. So again, kind of visualizing this fossil fuel use, factories and refinement, landfills, deforestation, agriculture, all of the above is going to be human-caused sources of greenhouse gases emission into our atmosphere. When we're looking at what's actually kind of causing all of that harm, when we're looking at methane to my top graph, nitrous oxide, my middle graph, and then carbon dioxide, I put some arrows next to where we see the biggest sources of this release. So we got methane up here. What we're seeing is livestock, right? Livestock is going to be a big one because, again, of that gut bacteria going through that digestion, it is going to be producing methane as a byproduct. Nitrous oxide, also agriculture, thinking about our fertilizer that is going to have, remember, NPK. Those are the 3 limiting nutrients that we are going to be increasing through industrial fertilizers. So because we have nitrous oxide, that's going to be coming from those agricultural soils, but also combustion as well. Think about acid rain. Fossil fuels used for energy, so oil, gas, petroleum, coal, all of that is going to be essentially the biggest source of carbon dioxide. And again, that is 100% human cause. When we're looking at accidental leaks of natural gas, cement manufacture, municipal solid waste, not really huge sources. So when we're trying to think about, okay, we see these raising temperatures, we see this global changes, how do we try to combat all of this? These are the big three that we're going to be kind of focusing our efforts on. I did want to break things up with a joke. What sound does a bird's phone make when it's ringing? Well, of course, it's going to be wing, wing, wing. Okay, let's keep going. Okay, so now we're talking about historic CO2 concentrations and why we're actually concerned about this. This is a kind of doom and gloom, but I promise you guys that there will be some positive endings to this presentation today. So when we're looking at global concentration, it is undisputed, okay? Scientists are pretty much in 100% agreement that there are fluctuations of CO2, okay? That is unquestioned. We also see fluctuations in global temperatures, also unquestioned. What we are kind of in disagreement, though, is going to be essentially what are going to be the effects of that. But one thing that is undisputed is that we are seeing unforeseen increases in temperature and unforeseen increases in carbon dioxide levels. That is something that we're not seeing. Now, you might be looking at this and thinking, excuse me, oops, I went too far. 350,000 years ago, really? Like, we did not have any technology, / humans were not around, theoretically 350,000 years ago. How in the world do we know CO2 levels? I'm going to actually switch to order this so I can come back to this because I feel like this goes together. How do we know our CO2 levels from hundreds and thousands of years ago? It is crazy science. There's something known as ice cores. And there's actually another reason, but I want to talk a little bit about ice cores first. So ice cores, essentially we go to Antarctica where it's always freezing. And what happens is every time you got a layer of snow, okay, snow trickles down, the snow hits the surface and then it freezes, it forms ice, okay? Next snow comes, da-da-da-da-da-da-da, freezes on top. Next snow comes, da-da-da-da-da, freezes on top. So what you end up getting is essentially a series of ice layers that have been formed over thousands and thousands and hundreds of years. What scientists are doing in Antarctica is they're creating something known as an ice core. They drill down into Antarctic ice, they extract out essentially a tube of ice, and what they see is gas bubbles. These gas bubbles were created when the ice actually froze. And what happens is within these gas bubbles, or in these little bubbles formed in the ice from hundreds and thousands of years ago, we can actually extract out the air within those pockets, within the ice cores, and we can test that air. And that air essentially is a time capsule preserved from hundreds and thousands of years ago. We extract that air out, we test it, and we can then get an accurate estimate. I mean, it's still an estimate, but as accurate as we can get of what the CO2 levels were like 100,000 years ago, 200,000 years ago, 300,000 years ago. It's amazing. So this chemical analysis of these ice cores is how we can figure out what might have been CO2 emissions 200,000 years ago. We also can look at changes in species compositions. There's certain species that are actually only around in certain temperatures. And so when we can look at it, say, all right, what species were around? So we can look essentially at sedimentation. We can look at fossil records. We can look at fossil layers, kind of similar to ice, that has been formed over many, many years of sedimentation and compaction. And we can figure out, okay, these are, and I'm trying to figure out, it's a seashell. I've got my book here. Foraminifera. So it took me a second to find the name of those. Foraminifera. And so we can look at these and we can say, okay, this essentially species of Foraminifera is only found at X amount of temperatures. Okay, so I can essentially look at which fossils I find of Foraminifera over different time periods to get an estimate of what the temperature might have been at those certain time periods. I apologize that it took me a while to find that. What we're also looking at is changes in mean and annual temperatures in different regions. What I've got here, the darker the color, or the more red, I should say, the more warm the temperature looks like on here, is what the change in degrees Celsius. What we're looking at is essentially looking from 2016 to 2020 compared to 1951 to 1980. So we are seeing an overall increase in many parts of the world positively. So anything that's blue, we actually see a decrease. So we do see some patches of ocean water. We did see some decreasing from 1951, 1980 range to the 2016, 2020 range. But holistically around the world, what we're seeing is an average increase in temperatures in degrees Celsius, which I'm sure we've all been feeling, especially here in Texas. Putting all this together, we can then also project kind of what we think that there might be some changes in temperature in the future as well. So right now we got 2020, 2029, kind of where we're at right in this range here on the left. And these are our different projections. If we see a low increase in CO2, if we see a moderate increase in CO2, or if we see a major increase in CO2, those are 3 different scenarios to take us to 2090 to 2099. Can you imagine 2090, 2099? Amazing. But what we're seeing these are 3 different projection maps, a kind of like best case scenario to worst case scenario, essentially. But this is kind of what we're looking at over the next couple days. Again, lots of doom and gloom. I promise there is going to be some positive slides at the very, very end of our presentation. What are the consequences to living organisms when we're seeing those overall increases in global temperature? Again, increase in global temperature due to the increase in greenhouse gas concentration, especially CO2, which is greenhouse effect. That's creating that global warming. Global warming can then cause these overall raising in average temperatures around the entire planet. Consequences. Think about growing seasons for animals or growing seasons for plants. Think about habitat ranges also for animals. We've talked about how there is a fundamental niche and a relays niche for all living things. One part of that fundamental or relays niche is temperature. All organisms have an ideal temperature range that they like to live within. So if we have overall temperature increases, that's going to affect the range of where animals live. A lot of organisms are going to be moving up north, or some animals may be losing their entire habitat entirely. Think about polar ice cap melts, right? That is a major habitat for many of our Arctic organisms. So we're thinking about changes in range that organisms are, especially animals, are occurring in. We're also thinking about alterations in the growing season for a lot of our plants. Humans as well. Humans may have to relocate if the temperatures become really dire in some areas. Also, we're thinking about increase in temperatures means that mosquito ranges can also increase as well. We also can think about economic consequences. If your entire way of life or your entire one big part of your area's economy, I gotta wrap this up. One big major part of your area's economy is ski resorts, skiing, snowboarding. Come visit the Alps. That is going to have some major consequences to our economies that are based on tourism and based on this Arctic wonderlands, for lack of a better words. Okay, we're going to keep going in just a second. All right, let's keep going. I got glasses on now. So we're also thinking about consequences of global systems as well. A lot of this you've probably already heard of, but with rising temperatures, especially due to our increase in greenhouse gas concentration, what we're going to see primarily is going to be a decrease in polar ice cap area. We're also going to see melting of permafrost in our taiga areas, and then we're looking at our boreal forests as well. This again releases further methane gases. We're also going to see sea level rise. We're going to talk through that and why this is essentially occurring in just a couple of slides. Increase in heat waves. I know here in Texas, we've been especially feeling that during our summer months. More dramatic cold spells as well during the winter. So essentially, we're seeing greater or more intense fluctuations from high to low during the winter and the summer months. Increase in storm intensity and shift in the global ocean current. So think about our thermohaline circulation, our underwater global currents that are happening in our oceans. That is all temperature driven, right? The cold water sinking, the warm water rising, kind of mixing everything up. So if you have overall changes in temperatures, that's going to affect the thermohaline circulation and our global ocean currents as well. So, not good. So sea level rise, we're going to talk about this a little bit further in class. I'm not going to touch on this too much, but essentially the big thing that's going on in sea level rise is we are seeing an increase in our overall level. And there's satellites that are actually going to be essentially pinging. They're floating, they're flying above the Earth's atmosphere, and they are pinging to see exactly, to measure what is the sea level rise. We'll talk about what exactly is the machine that NASA is utilizing to get these overall sea level measurements. But we're saying that overall, especially compared to, let's say, the center of the Earth, we are seeing a dramatic increase in how high our sea level is essentially reaching. A lot of this, though, occurs from land-based ice, and it's really important. I'm going to try to, I don't know if you actually see me moving my head when I do that, but it's coming from land-based ice. So if you think about water displacement, we have land-based ice and we have sea-based ice. Sea-based ice would be our floating ice masses, our glaciers, or icebergs, I should say, icebergs that are floating in the water already. When those melt, it is going to increase the volume of the water a little bit, but not too much, because if you're thinking about it, it's already in the water. So it's already completing or going through water displacement. But whenever I have land-based ice, this is glaciers that are above the water level itself, when those melt, we are actually adding in volume of that water. So it is a lot more detrimental. I'm sorry, I don't know if I'm able to get it so that you guys can not, oh dear, that's not what you needed to see. Oh my gosh, sorry. Everything's falling apart. But it is supposed to say down here, more detrimental than melting sea-based ice due to water displacement. That's what that's saying there. So again, we're going to talk about this more in class. And if you're thinking about a lot of our coastal ecosystems and our coastal communities, such as New Orleans, we're thinking about Venice, we're thinking about our island communities that are right there on the coast. Yes, it's only increasing at millimeters per year, which doesn't sound like a lot, but if you add it up over time, if our effects are being exponential over the years, then that's going to affect our aquatic or our coastal communities as well. I did have to throw in a meme. Sorry, you did see it a little bit earlier. I don't know if this is in poor taste, but I just thought it was funny. All right. So controversy of climate change, right? It is kind of a hot topic issue. So one thing I want you guys to kind of understand is that what is not in dispute among scientists is that greenhouse gases are increasing over time and that this will lead to global warming. Yes. But what we're not sure about, though, is how much the actual changes are going to occur worldwide holistically when we're thinking about our global climates due to feedback loops, which we're going to unpack in just a little bit. So hold tight on feedback loops. But one thing I just wanted to kind of like leave you guys with is that, yes, like our greenhouse gases are increasing. I think that is like indisputable. Our temperatures are increasing. What we're not sure about, though, is what are going to be those long-term lasting effects. Which I'm sure all of us, including myself, are very interested in seeing what are going to be those long-term lasting effects. So again, feedback loops, I'm not going to lie to you guys, people get these mixed up every single year. I believe in you guys, though. I think that you are strong, wonderful, independent, amazing students, and I think you can do this. We have positive and negative feedback loops. Positives on the left, negatives on the right. What students a lot of times will think is they're thinking, oh, positive is good, negative is bad. Yes, in a lot of cases, not so much in feedback loops. When you hear positive, I want you to think intensifying. When you hear negative, I want you to think reducing or homeostasis, keeping things in balance or keeping things in check. So positive feedback loop essentially is intensifying or increasing a situation. Things are getting worse or more dramatic in a positive feedback. For example, higher levels of CO2 promote higher temperatures, these higher temperatures. So that is my stimulus. The first thing that happened is I have an increase in temperature. This increase in temperature leads to faster decomposition. Faster decomposition boosts the rate of CO2 being added to the atmosphere. More CO2 means higher temperatures. So essentially, my initial stimulus, what happened, the higher CO2 levels led to a further release or a further increase of CO2 levels. Again, I'm intensifying something. Childbirth is another big one. Whenever it's time to have the baby, oxytocin is a hormone that is being released from your brain. Oxytocin says, hey, it's time to start pushing, essentially. And so your body actually goes through, you've probably seen, the cramping, right? You've probably seen all the birthing pains. And so essentially it's pushing down. The pushing of the baby itself, the physical pushing, actually feedbacks to release more oxytocin. More oxytocin is released, more pushing occurs. Again, that baby is then being pushed against the walls. Those walls then shoot back more oxytocin. Again, a positive feedback loop, intensifying or increasing the situation. Negative feedback loop, think homeostasis, bringing things back into balance. Okay, so I've got my stimulus here. Increased atmospheric CO2, increased plant growth, right? Plants need CO2 to go through photosynthesis. If I have more CO2, that's going to increase plants going through photosynthesis. If I then have more plants are then going to go through more photosynthesis, decreasing the amount of CO2 in the atmosphere. Okay, so I had a stimulus, increased CO2, but that increased CO2 led to a decrease in CO2. Thermostats are another example of negative feedback loops. It gets really hot in here. Hot air is the stimulus. AC kicks on. AC then goes through a series of cooling processes that brings that temperature back down. It's a regulatory system in my negative feedback loops. So again, positive feedback loops, think intensifying. Negative feedback loops, thinking bringing things into balance and regulating. So putting it together, positive feedback loops. So we do know, again, pretty undisputed, is that there is an increase in CO2. And when I have an increase in CO2, it causes a greater capacity of warming because CO2 is one of our major 5, 6 greenhouse gases. When the Earth experiences higher temperatures, the oceans warm. Oceans cannot contain as much CO2 gas. As a result, they release more CO2 gas into the atmosphere. More CO2, more greenhouse gas effect, more global warming, more CO2 being released. Again, this is another one of those positive feedback loops. Good news. Okay, we do have a couple final slides to wrap us up today. They are all good news, though. One of them is the Kyoto Protocol. The Kyoto Protocol happened in 1997, so quite a while. But a lot of world leaders from around our nations around the world went to Kyoto, Japan, and they're like, hey, okay, things are not going great right now. How can we attempt to reduce what's going on? How can we try to counter out the effects of global warming? So the agreement was that we were going to look at all of our industrialized, our developed nations, and we need to reduce our 6 criteria air pollutants. We need to look at as well our major greenhouse gases, really. So we're looking at our CFCs, my nitrous oxides, my sulfur dioxides, and of course my CO2 levels. And they needed to reduce those. Kyoto Protocol is still in effect. It is, again, focusing mostly on our industrialized developed nations. If you're thinking back to chapter 7, human populations, think about it, right? We talked about how developing nations have much greater emissions of CO2 and other greenhouse gases and fossil fuel consumption than my developing nations. So developing nations were not as affected, but of course my developed nations, they were kind of put under the microscope for the Kyoto Protocol. So good thing that's still in effect. Another last kind of piece of good information is we are looking a lot of ways into trying to trap a lot of the CO2 that is in our atmosphere. I mean, we're at unprecedented levels, so let's find a way to just extract it out. If we can't find a way yet to eliminate what's being produced, let's take what's already there and then break it down. So one of them, peat moss. Peat moss is actually a huge, essentially it's a plant, right? Moss, peat moss, and it has an amazing carbon storing capability. We're going to talk about this a lot in class. Bogs are amazing ways of storing carbon dioxide. So rather than cutting down trees, rather than turning bogs and swamps and wetlands into agricultural lands, let's keep them as they are, as moss and grass and bog, and that is going to then hold a lot more carbon dioxide than grass. Grass and agricultural fields holds very little carbon compared to our other powerhouses. Other ways you can actually extract CO2 out of the atmosphere, either right as it is being created at the manufacturers themselves, or from actually then taking it after it's been burned and extracting it out of the atmosphere. You can put it in agricultural soils. Again, taking our agricultural land, turning it back into forest. That's a huge way of kind of bringing back some of that carbon dioxide out of the atmosphere. We're also looking at trying to get rid of it at the source. So here's kind of a way that we can look at this. Again, one way is we can add in nude vegetation, photosynthesis, powerhouses, pulling out that CO2 from the atmosphere. We could also extract it out and essentially pump it into the ocean floor, pump it underground into rocks. You can, once you have an empty oil reserve, okay, now we have a pocket underground, let's fill it with carbon dioxide. Same thing, I have an empty coal mine. Okay, we're not going to be using it for any time. Let's pump it with carbon dioxide. Again, we're trying to take it all out of here, and we're taking it with our CO2 scrubbers as well. You reached the end of chapter 19. So my question or my riddle for you is, what is a question you can never answer yes to? We'll talk about that in class. But I want to say you guys are amazing. I'm proud of you. Have a wonderful, wonderful day. I'll see you guys in class. Take care.